Hello everyone, today I will present a complete machine learning project developing a binary classifier to predict pre-diabetes or diabetes using 110,000 health survey responses. I will demonstrate how data engineering and algorithmic optimization can break through classifier performance bottlenecks. First, load the data. The training set contains 110,000 samples with 22 features, and the test set has about 11,000 samples. During the EDA phase, after confirming no missing values, I focused on the distribution of the target variable diabetes binary. The plot reveals a severe class imbalance. 86% are healthy individuals, and only 14% have the condition. For the correlation heat map and metrics, I observed that general health and high blood pressure have the highest correlation with the target variable, which guided our subsequent feature engineering efforts. To improve model performance, I didn't feed the raw data directly into the model. In step 3 of the code, I implemented advanced feature engineering. I found that individual binary features lacked sufficient signal. Therefore, I created 6 combined features such as risk score and BMI age interaction. By incorporating medical knowledge and nonlinear relationships between features, I enable the model to capture higher order information not directly expressed in the raw features, thereby enhancing its representational power. Next, I performed data standardization and used PCA for dimensionality reduction. I reduced the feature space from 28 to 20 dimensions while retaining over 95% of the variance. These steps effectively reduce the feature redundancy and mitigated overfitting risks. To validate the effectiveness of our engineered features, I compared the feature importance from logistic regression and random forest. The random forest importance ranking clearly shows that our newly created features, BMI aged interaction and health decline index, ranked first and sixth. This proves that our constructed features contain crucial information for predicting diabetes. To address 86-14 class imbalance, I initially tried mode but found it generated unrealistic synthetic samples, such as high BP equal to 0.43, which harmed the precision. Our final and most effective strategy was to retain the raw imbalance data using the model's native class weighting and apply decision threshold tuning. This preserves real-world distribution while avoiding synthetic noise. Next, I moved to the core phase, model development and tuning. We compared 3 different models, LightGBM, a neural network, and auto machine learning. I selected LightGBM as our champion model for its speed, built-in imbalance handling, and noise robustness. For tuning, I used randomized search CV with F1 score as the objective across 7 hyperparameters. Notably, I tuned the mean child samples to filter isolated samples and reduce false positives, a key noise reduction technique. Post-tuning, our F1 score improved significantly. I then performed optimal threshold tuning on the validation set, as the default 0.5 threshold is unsuitable for imbalanced data. For iterating through all thresholds to maximize F1 score, I identified a golden threshold of 0.6485, achieving a final F1 score of 0.5 4741. For comparison, I built a simple 3-layer neural network with class weights to handle imbalance. It performs reasonably well, but its F1 score was slightly lower than the finely tuned light GBM. I also introduced auto machine learning as a benchmark. Within 2 minutes, auto machine learning tried several models and ultimately selected XGBoost. While its ROC-AUC was the highest, its F1 score was significantly lower than our tuned light GBM. This is because Auto GBM's default optimization metric was AUC, which focuses on overall ranking ability, not directly on the precision of the minority class prediction. This result highlights that automated tools cannot replace customized tuning targeted at a specific business objective, such as optimizing for F1 score. To assess model fit, I didn't rely solely on a simple train-test split. During hyperparameter tuning with randomized search CV, I exploit k-fold cross-validation. This strategy ensures consistent model performance across different data subsets, significantly enhancing the performance stability on unseen test data. The learning curves from our retrained model confirm the effectiveness of this approach. As shown in the left chart, training log loss steadily decreases while validation log loss stabilizes after around 250 iterations, indicating no severe overfitting. The right chart reveals that validation AUC plateaus at approximately 0.834 after 300 iterations, while training AUC continues to rise marginally, a clear sign that further training would only benefit the training set without improved generalization. This validates our early stopping decision, as the model achieves optimal performance precisely when validation metrics peak. Our light GBM model correctly identifies 1,814 true diabetics but missed 1,214 patients and falsely flagged 2,811 healthy individuals. In a long default prediction scenario, a false positive represents opportunity cost, while a false negative leads to direct financial loss. Since false negatives carry higher cost, I abandoned the default 0.5 threshold, instead selecting the golden threshold on the PR curve that maximizes F1 score. This trade-off significantly improved recall while achieving a mathematically optimal balance between medical risk and the practical screening value. With additional time and resources, I could pursue 3 key improvements. First, incorporating external data beyond physical exams, such as macroeconomic indicators or credit data, would provide valuable socio-economic context critical for enhancing credit risk models. Second, I would implement robust production monitoring to track prediction distributions, feature stability, and business metrics in real time. If performance degrades, we must detect data drift and promptly retrain the data when concept drift occurs. Third, I could explore sophisticated architectures like Tab Transformer, a deep learning model designed for tabular data that excels at handling categorical features and capturing complex nonlinear relationships. That's my presentation. Thank you.